Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. Human beings communicate each other using natural languages such as English, Malayalam, Hindi or any other. These languages are made of words and letters. Communication becomes successful when there is a common language for interpretation and when both parties understand each other. Then, how do we communicate with a computer or any other digital system? Whether the computer understands the language we use, we interact with a computer using different media such as text, audio, image, etc. How does an electronic machine interpret these? How is it internally stored? The computer does not understand the words and numbers of the input we give. Rather, those are translated into numbers and stored in a coded form. Number systems play a vital role in the computer system architecture. This module introduces the commonly used number systems and their relationships. The broad classification of number systems are non-positional number systems and positional number systems. What is non-positional number system? Do you remember how did you learn counting? How did you play by counting? Counting by fingers. When we had to count beyond 10, we started using stones, pebbles, pearls or sticks to indicate the values. We were not using digits there, only symbols, where each symbol has the same value irrespective of when and where it is kept. This system of counting is known as non-positional number system. The characteristics of non-positional number systems are: 1. It uses the symbols such as 1 stick for 1, 2 sticks for 2, 3 for 3, 4 sticks for 4, 5 sticks for 5, etc. The second characteristic is each symbol represents the same value regardless of its position in the number. And the third point, value can be found out by simply adding the symbols. The disadvantage of non-positional number system is that it is difficult to perform arithmetic with such a number system. Also, counting large numbers becomes very difficult. To overcome these problems, positional number systems are developed. Okay? What is positional number system? In our daily life, we come across a large set of numbers for different purposes. Have you noticed how many digits do we use there? We use 10 digits from 0 to 9 and all other numbers are made of these 10 digits. This is decimal number system, which is an example for a positional number system. Here, the base of this number system is equal to 10 because it contains 10 digits. As the name indicates, in positional number system, the position plays the main role. Consider the number 111. The value of rightmost digit 1 is just 1, whereas the value of leftmost digit 1 is 100. Though the digits are same, all ones, their values are different as they appear in different positions. For every positional number system, there will be a base or radix and a set of predefined digits. These digits represent different values depend on their position in the number and base of the number system. What are the characteristics of positional number system? The first point is it uses symbols or digits. For example, in decimal number system, we use the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Second point is each digit represents different value depends on the position they occupy in the number. In the number 111, Each one takes a different value, different positional value. So, the value of each digit is determined by 3 factors. 1. The digit itself. 2. The position of the digits in the number. And 3. The base of the number system, which is the total number of digits in the number system. And the maximum value of a single digit is always equal to 1 less than the value of the base. In decimal, the base is 10, and we know that the last digit is 9, which is 1 less than 10. Hope it's clear to you. During this session, we are going to discuss 4 important positional number systems. They are decimal number system, binary number system, octal number system, and hexadecimal number system. Decimal number system is the one we are most familiar with. 10 fingers, 10 digits. Very easy to understand, right? As I said earlier, it has 10 digits from 0 to 9. So, its base is equal to 10. Any number that we form in this number system will be a combination of these digits or symbols. Each position of a digit represents a specific power of the base, that is 10. For example, the number 1239 can be represented in its positional notation as 1 into 10 cube plus 2 into 10 square plus 3 into 10 raised to 1 plus 9 into 10 raised to 0. The positional value of the rightmost digit 9 is 10 raised to 0. The next digit 3 is 10 raised to 1. Positional value of 2 is 10 square and 1 is 10 cube. And that's why we say units place, tens place, hundreds place, thousands place, etc. So, 1239 can be written as 1 into 1000 plus 2 into 100 plus 3 into 10 plus 9 into 1, which is 1000 plus 200 plus 30 plus 9, which is equal to 1239. For a fractional number, the positional values are in negative powers of 10 that decreases towards right. For example, consider the number 12.625. This can be written as 1 into 10 raised to 1 plus 2 into 10 raised to 0 plus 6 into 10 raised to minus 1 plus 2 into 10 raised to minus 2 plus 5 into 10 raised to minus 3. Okay? Dear learners, please observe how the base of the number system, that is 10, is used in the formation of a number. Any number in the decimal number system can be decomposed into a sum of product of each digit and its positional value. In general, a number of base r can be expressed in the form a n r raised to n plus a n minus 1 r raised to n minus 1 plus a n minus 2 r raised to n minus 2 plus etc. plus a 2 r square plus a 1 r plus a naught r raised to 0 plus a minus 1 r raised to minus 1 plus a minus 2 r raised to minus 2 plus etc. plus a minus m r raised to minus m. When you understand the concepts of any one number system, it's easy to learn other number systems. Next, we are going to study binary number system. The binary number system is used to store information in electronic format. All digital equipments, smart and intelligent devices use this system. As we know, in digital electronics, all the operations are carried out using 2 voltage levels, high and low. And it is easy to translate binary data to electronic signals. High is usually represented by 1 and low by 0. This is the significance of a binary number system in digital computing. The binary number system has only 2 symbols or digits, 0 and 1. Hence, its base is 2. What is the maximum value of a single digit in binary? 1 less than the value of the base, that is 1. In binary, Each position of a digit represents a specific power of the base 2. That means in the binary number 1 0, 0 is in 2 raised to 0 position and 1 is in 2 raised to 1 position. Now let's see how a binary number is formed. The first binary number is 0. Next is 1. What is next? Let's try to bring out this from a comparison with decimal numbers. In decimal number system, we write numbers from 0 to 9. Single digit numbers, all in ones position. After 9, to get the next number, move on to the tens position. There we start with 1 in tens place and restart with 0 in the ones place. So we get 10, 11, 12, etc. up to 99. Then include one more position, hundreds place, and continue with 100, 101, 102, etc. Likewise, we shall count the numbers in binary too. After 0 and 1, move on to 2 raised to 1 position. Then we will get 1 0 and 1 1. Then move on to the position 2 square, which gives us 1 0 0, 1 0 1, 1 1 0, 1 1 1, and so on. The table given here shows you the first 16 binary numbers and corresponding decimal values. For decimal 0, it is 0 in binary. For decimal 1, it is 1 in binary. Then for 2, it is 1 0. For 3, 1 1. Then for 4, 1 0 0, and it goes on. And finally for 15, it is 1 1 1 and 1. Each digit in binary 0 or 1 is known as binary digit, in short bit. While observing the binary numbers in the list, we understand that with 2 bits only 4 patterns are possible: 0 0, 0 1, 1 0 and 1 1. With 3 bits only 8 numbers from 0 to 7. And with 4 bits 16 numbers, the numbers from 0 to 15. In fact, any decimal number in the range 0 to 2 raised to n minus 1 can be represented in binary form using n bits. In other words, using n bits, we are able to form numbers from 0 to 2 raised to n minus 1. What about the positional values of a binary number? The base of the binary number system is 2, and hence the positional value is increased or decreased by the powers of 2. To illustrate, let's consider the number 110.101. The positional value or weight of each bit can be written as it is shown here. For the first bit 1, the weight is 2 square, then for the next bit it is 2 raised to 1, then 2 raised to 0, then 2 raised to minus 1, 2 raised to minus 2 and 2 raised to minus 3. From the decimal point towards right, the positional value is decreased by the powers of 2. So, it is 2 raised to minus 1, 2 raised to minus 2 and 2 raised to minus 3. From the decimal point towards left, the positional value is increased by the powers of 2, and hence it is written as 2 raised to 0, 2 raised to 1, 2 raised to 2, etc. The first digit in the integer part has 2 raised to 0 weights, then 2 raised to 1, 2 square and so on. The first digit in the fractional part has 2 raised to minus 1 weights, then 2 raised to minus 2, 2 raised to minus 3 and so on. Now, let us write the binary number 101101 in its positional notation. The positional value of least significant bit, that is the rightmost 1, is 2 raised to 0. For the next left bit, it is 2 raised to 1, and for next it is 2 square and so on. Then the binary number 101101 can be represented in its positional notation as 1 into 2 raised to 5 plus 0 into 2 raised to 4 plus 1 into 2 cube plus 1 into 2 square plus 0 into 2 raised to 1 plus 1 into 2 raised to 0. When you calculate the right hand side, you will get a value which is the decimal equivalent of this binary number. So, here 101101 equal to 1 into 32 plus 0 into 16 plus 1 into 8 plus 1 into 4 plus 0 into 2 plus 1 into 1, which is equivalent to 45 in decimal. The base value is commonly shown as a subscript to the number, and it is a good practice too. So, we write 101101 to the base 2 is equal to 45 to the base 10 in a subscripted fashion. Next, we will talk on octal number system. The word octal sounds the number 8. Yes, 8 is the base of this number system. And the 8 digits are 0, 1, 2, 3, 4, 5, 6 and 7. Octal number system has a total of 8 symbols or digits from 0 to 7. Hence, its base is 8. The maximum value of a single digit is 7, that is 1 less than the value of the base. Each position of a digit represents a specific power of the base 8, like 8 raised to 0, 8 raised to 1, 8 square, etc. As in the case of decimal and binary, we can generate numbers in octal number system too. It starts from 0 and reaches to 7. A new bit position is included here. So, the next number becomes 10, then 11, 12, etc. 17, followed by 20, 21, 22, etc. The table lists the octal and binary equivalent of the numbers from 0 to 16. The decimal value 0 is represented as 0 in binary, 0 in octal, 1 it is the same, 2 in binary it is 1 0, but in octal it is again 2, and it goes on, and if it is 6 in decimal, 110 in binary and 6 in octal. And when it comes to 8, in binary it is represented as 1000 and in octal it is 10. For 9 it is 11, for 10 it is 12, etc. And for 15 in binary it is 1111 and octal representation is 17. How do we represent an octal number in positional notation? Consider the number 4273 to the base 8. This is represented in its positional notation as 4 into 8 cube plus 2 into 8 square plus 7 into 8 raised to 1 plus 3 into 8 raised to 0, which is equal to 4 into 5 12 plus 2 into 64 plus 7 into 8 plus 3 into 1. The result of this would be the decimal equivalent of 4273 to the base 8. Binary number appears to be long strings of zeros and ones, and so it is difficult to transcribe without errors. You might have noticed that to represent each octal digit, we had to use 3 bits. So, octal equivalents are much shorter. It is also easy to remember and has a straightforward way of conversion to or from binary. Then, the last positional number system we are going to learn today is hexadecimal number system. Hexadecimal number system is a positional number system having 16 symbols or digits 0, 1, 2 up to 9, then A, B, C, D, E and F. As it consists of 16 digits, its base is 16. The numbers 0 to 9 in hexadecimal are equivalent to 0 to 9 of decimal number system. The symbols A to F represent the decimal values 10, 11, 12, 13, 14 and 15 respectively. The maximum value of a single digit is 15 because base equal to 16, base minus 1, 16 minus 1 equal to 15. Each position of a digit represents a specific power of the base 60. In our daily life, we come across several situations where we use hexadecimal numbers. For example, we receive error messages from digital devices in hexadecimal format. Then color on web pages, MAC addresses, etc. all are represented using hexadecimal numbers. It's a more compact representation of a number. Numbers in hexadecimal number system can also be generated by the method we followed for other 3 number systems. The table given here lists the first 20 numbers in hexadecimal number system and its relation with other number systems. From the table, the decimal value 0 is represented by 0 in all other 3 number systems. For 1, it is the same. The decimal value 2 is represented by 10 in binary, 2 in both hexadecimal and octal. And when you go through the table, finally when it reaches to 9, the decimal representation is 9, binary representation is 1001, octal representation is 11, hexadecimal representation is 9. And for 10 in decimal, the binary representation is 1010, octal representation is 12, and see the hexadecimal representation is A. And it goes on like this. Finally, for 20, the representations in binary 10100, representation in octal is 24, and for hexadecimal it is 14. Let us also illustrate one problem of representing a hexadecimal number in its positional notation. Consider the number 2C6.1D to the base 16. This can be written as 2 into 16 square plus C into 16 plus 6 into 16 raised to 0 plus 1 into 16 raised to minus 1 plus D into 16 raised to minus 2. To proceed with, we need to know the decimal equivalents of hexadecimal digits C and D. They are 12 and 13 respectively in decimal form. Continuing from the previous step, then we write 2 into 256 plus 12 into 16 plus 6 into 1 plus 1 into 0.0625 plus 13 into 0.0039, which is equal to 512 plus 192 plus 6 plus 0.0625 plus 0.0507. And the final result is 710.1132 to the base 10. Hence, we get the decimal equivalent of a hexadecimal number. This method is widely used for converting any number of base r to decimal. We are going to discuss it in the next session. The most suitable number system for digital computing devices is binary. Though binary causes to have too many bits in a number, it can be represented in hexadecimal with fewer characters. Each hexadecimal digit corresponds to 4 binary digits. For example, 10011110 is a binary number which can be expressed in hexadecimal as 9E. So, hexadecimal number system is very useful to map the information stored in binary. We have reached to the end of the session. To summarize, the 4 number systems commonly used in computer system architecture and associated fields are decimal, binary, octal and hexadecimal number system. Normally, we use base 10 or decimal number system in our day-to-day life. Binary computation is mandatory for a machine that deals with only 2 states, low voltage and high voltage, or 0 and 1. But representing large numbers in binary is too difficult to read and manipulate. So, the hexadecimal representation of merging 4 binary bits and octal representation of merging 3 binary bits came into pictures. It is good to know that conversion between these number systems can easily be carried out. which is the point of discussion in the next class. Thank you for watching. See you in the next session. Bye.